Hello, this is video 59. I'll be talking about Newton's second law for rotational motion, so how Newton's second law applies when objects are rotating. So it turns out that it has the exact same form as before. If you remember, before it used to be A equals the sum of the forces over m. Well, now the angular acceleration is directly proportional to the net torque and inversely proportional to the moment of inertia. So this makes sense because alpha is the rotational equivalent of A, torque of the force, and I of the m. So if you look, for example, at this picture here, we have a bucket falling down, and it's causing the reel here to rotate. So what's happening is that there's a force applied to the reel, and that causes rotation, so that means there's a torque exerted on the reel, which causes it to have some angular acceleration. So just like a force causes an acceleration, a torque causes an angular acceleration. Now, before, when we did this type of problem, this may remind you of the Atwood machine, where you had two masses over a pulley. But when we did the Atwood machine, we said, let's ignore the mass of the pulley. But now we don't ignore the mass of the pulley or the reel, because in reality that mass affects the rotation. If you have a very thin reel, it might rotate very quickly when the bucket pulls it down. But if you have a very thick one that's heavier, it could be that the bucket barely even causes any rotation. So what we're looking at is the effect of a torque in producing an angular acceleration. Let's look at this one example for this video, the angular acceleration of a falling pole. So in the caber toss, I hope that's how you pronounce that word, a contest of strength and skill that is part of Scottish games. Contestants toss a heavy uniform pole, landing it on its end. So this person here just tosses pole, it landed there, and of course it's going to start falling down. So here, when it has just landed, it's tipped by 25 degrees from the vertical. It's starting to rotate about the end that touches the ground. Estimate the angular acceleration. It says estimate because we are assuming that it's a uniform pole, that the mass is evenly distributed. But in reality, there's not going to be perfectly even distribution of the mass. We need uniform distribution of the mass in order to be able to use our equations for moment of inertia. So this is a rod that is being rotated about the end. So if we go back to the equations that we just saw, that means that the moment of inertia is going to be 1/3 ml squared, which applies for a rod being rotated about the end. So this is how you use this table. Now we're ready to do this problem. So we're going to, let me go ahead and write down what we are given here. The length of the pole, which is 5.9 meters, and then the mass, which is 79 kilograms. And I tend to use capital letters for mass when we're talking about an extended object that we care about the size and shape, versus when we have a little particle, I usually use a lowercase m. So we can draw a picture now so that we have more room here. So we have the rod, and I'm exaggerating the angle, but the angle is 25 degrees with the vertical, is what it says. So it's going to rotate. So we have to figure out, well, what force is producing that torque that is causing it to rotate and have some angular acceleration this way. So it's going to be the weight of the object that is pulling it down. Now the weight of the object is going to act at the center. We'll see more about this in the next unit when we talk about center of gravity, but for now, just realize that if a rod is uniform, then the weight is going to overall act in the center. So that's going to be the force that causes the rotation. There's some forces here where that stick touches the ground, but forces at the pivot point don't cause any rotation because they have no distance from that pivot point. So we only care about the weight which is producing that rotation. So what we need to do is look at our equation that the angular acceleration equals the net torque over the moment of inertia. We need to go ahead and calculate both things separately so that we can plug them in to find the acceleration. So the moment of inertia we said was 1/3 ml squared because it was a rod rotated about its end. So that's going to be 917 approximately kilograms meters squared. And then the net torque is the torque produced by just this force. Since this object is diagonal, I'm going to use the FD definition. So the way that we're going to use this one is we extend that force line, and then we find the shortest distance from the pivot to that force line, which is this horizontal distance right here. That's our D. Now we have the length of the rod, and we said that the weight acts halfway. So that means that this distance right here is going to be half of 5.9, which is 2.95 meters. And since we have this angle right here, which is 25, which is the same as this one, we know that D is opposite, so it's going to use the sign. So D is going to be 2.95, the hypotenuse, times sine of 25 degrees. And the FG is the weight, so now that means that the net torque is going to be mg times d. So we're going to go ahead and plug in those numbers. 79 times 9.8 times 2.95 times sine of 25 degrees. And for all of that, I got 965 Newton times meters. Now the rotation here is counterclockwise. If you fix this point, it's causing it to rotate this way, which is counterclockwise. That's a positive torque in the same direction as the acceleration. So now we're ready to plug in our values. 965 divided by 917, and that's going to give us 1.05 radians per second squared, which is the unit of the angular acceleration. So hopefully you see the relationship between this form of Newton's second law and the linear form. Instead of finding the net force that causes an acceleration, we have to find the net torque that causes an angular acceleration. And in the problems we're going to do in this class, we're going to limit our problems to just one force causing that net torque. If there were more than one force, then you just have to add up all of those torques together.